This is the answer to the 1991 AP question. It has this little graphic here. This is a standard graphic about the first ionization energy. So I'd like to try to go through this. The overall question says, this diagram up here shows the first ionization energies for the elements from lithium to neon. So explain a couple of these ideas in terms of atomic structure. In general, there's an increase in the first ionization energy from lithium to neon. So as you go across, you can see that this goes up and up and up. Part B, the first ionization energy of boron is a little bit lower than that of beryllium. So explain why you have that little jag in the uphill thing. Third part, the first ionization energy of oxygen is a little bit lower than nitrogen. And the last thing is predict how the first ionization energy of sodium compares to lithium and neon. If the first part, if we go back and say, well, what happens to the trend as you go across, is you can see as you go across any row of the periodic table that the ionization energy tendrily goes up. And the idea here is that as you get more and more protons in the nucleus, then there's a greater attraction for the electrons, and since there's a greater attraction for the electrons, it's going to be more difficult to pull those off. So we're trying to find the idea that there's more protons, that's going to get a greater attraction. And therefore, larger ionization energy, which is the energy it takes to remove one of those electrons. Now this is all just, we know that positives and negatives attract each other. And if you get more and more positives, you can have a greater attraction for those negatives. Part B. This is talking now about boron is lower than beryllium. And to really understand this, we need to kind of go back and say, okay, well, what does the electrons look like in beryllium and boron? Okay, beryllium is number 4, so it has 1, 2, 3, 4 electrons. And boron has 5. 1, 2, 3, 4, 5. So what happens here is the electron that we're trying to remove from boron is actually coming from a 2p orbital, where this is coming from a 2s orbital. So that's one big idea here. So for boron, it's coming from 2p. For beryllium, it's coming from the 2s. And because the 2p orbital is a little bit higher energy than the 2s orbital, then it's a little bit easier to remove that electron than it would be from a 2s orbital. So that's the big idea. So we get 1 point for saying that we realize that the beryllium and the electrons coming from the 2s, boron 2p, and that since the 2p orbital is higher energy than the 2s, it's a little bit easier to remove the electron. Now my student said, okay, this is true for this guy, so it's going to be a little bit easier to remove because of the fact it's a higher energy orbital, but isn't that also true for carbon and for nitrogen? When you put another electron right here, another electron right there, isn't that the same situation? And the answer is yes, it's exactly the same situation. And if we take that into account, then we can see that this trend, our original trend, continues on just like we expected. And wouldn't that also be true for the next 3 atoms? And the answer again is yes. So this is actually going to go up a little bit. So here's our idea for boron and beryllium. Boron's a little lower because the electron is coming from a higher energy orbital, easier to remove. Now for part C, why is nitrogen and oxygen? That's where we're going to concentrate. So why is oxygen a little bit lower than nitrogen? Now just like we did before, it's important that we get our pictures. So nitrogen has 7 electrons, 1, 2, 3, 4, 5, 6, 7. And oxygen has 8, 1, 2, 3, 4, 5, 6, 7, 8. Now the key idea this time is this electron that we're going to remove is coming from a filled orbital, whereas the electron we're going to remove in nitrogen is just a half-filled orbital. So the oxygen, this electron, is going to be a little easier to remove because there's electron-electron repulsion in the oxygen case that you don't have in the nitrogen case. So besides putting energy in to remove that electron, there's another electron inside there that is trying to push out that electron, so that makes it a little bit easier to remove. And then again, somebody pointed out, well, isn't that also true of fluorine and neon? And the answer is yes, that is true, because as we put electrons in here and in here for fluorine and neon, okay, they're also in doubly filled orbitals. So if we go back and get our trend again, we can see that it kind of adds up. Part D, okay, we're going to predict how the first ionization energy of sodium compares to lithium and neon. Okay, well, first ionization energy, the energy to pull off an electron. Well, sodium is going to be easier than it is for lithium, because sodium has more layers of electrons than lithium does. And so since there's more layered electrons, the electrons that we're trying to remove are actually farther from the nucleus than the electrons in a lithium. So it's going to be a little bit easier to remove sodium electron than lithium. Now over here on neon, neon is going to be much more difficult to pull off an electron than lithium, because we have more protons. So we can see what's going to happen is sodium is going to be easier. So sodium takes a smaller ionization energy than lithium, and then lithium is smaller than neon, so definitely sodium is going to be smaller than either lithium or neon. So the big overview is that there is a general trend upward for the ionization energy, because we get more and more protons. But once we get to boron, then we start putting electrons into a p orbital rather than an s orbital, and that's going to make it a little bit easier to remove, because the p orbital is higher energy than the s orbital, so we're starting from a higher platform. And that affects these three atoms, and it also affects these three atoms. And we can see what happens is when that does happen, then our trend basically is one big long line. Then we get back to the part where we say, well, once you get to oxygen, now we're pulling this one from a doubly filled orbital, and because it's a doubly filled orbital, there's electron-electron repulsion, making it a little bit easier to remove that. So if we take that into account, then we can see that we get back to our big trend. So we have our big overall trend that as there's more and more protons, it gets more difficult to remove an electron. Layered on top of that is, because we have electron-electron repulsion, this goes up a little bit, and because we're pulling things from the p orbital rather than the s orbital, then this one is changed a little bit also. So the look of the whole picture has to do with the electron-electron repulsion and the fact that we're coming from a p rather than a s orbital. That's it.